All right, well, hello. Good morning. Today we're going to do our second hour exam review. Now I hope that everybody printed the little mini prints. I included the study points for chapters 4 and 5 at the beginning of the mini prints. These are very nice because they condense everything down to just a few concepts or whatever that you have to remember and whatever. Remember, we will do this today on Monday. We will do the sample exam. And we'll hang around as long as you want, ask questions, make sure you got it, etc. Wednesday, we will have lab. And then Friday, we will have our exam. Any questions?
Not yet.
Not yet?
We got a note card again?
Yes, of course you do. You may not bring your first one though, but hang on to your note cards if you want, because for the final exam, you get to bring all 4. But by the time you get to the final exam, the first 3 are going to be so simple that you're never going to look at it anyway. But, all right, so here we go. Study points. Remember, a mole is simply defined as a number of atoms in 12 grams of carbon-12. 6.02 times 10 to the 23rd things in a mole. Remember, it's just a unit. It's like dozen. It just refers to a number. Avogadro told us that equal volumes of all gases at the same temperature and pressure, we'll do that later, have the same numbers of molecules. And that's where Avogadro's number come from. 6.02 times 10 to the 23rd, that's 22.4 liters of a gas. And at 1 atmosphere, 25 degrees centigrade, that contains 1 mole of that gas. If we take the formula mass of any substance, so molecular weight or average atomic mass on the periodic table, and we express that in grams, mass units, we refer to that as molar mass. So carbon-12, if we had exactly 12 grams of carbon-12, it would contain 6.02 times 10 to the 23rd atoms of carbon-12, and it would weigh 12 grams. Simple conversion. Moles times molar mass gives us mass. One that you will never forget. Mass divided by molar mass is moles. Pick one of these to remember, okay? Because you can always convert back and forth from the others. If we have moles and we want to do number, you know that 1 mole contains 6.02 times 10 to the 23rd things. So simply multiply the number of moles by Avogadro's number to get the number of things you've got. We talked about percentage composition. Basically, for percentage composition, you take a mole ratio for your compound, whatever your substance is. Take the mole ratio and convert it to a mass ratio. That's just multiplying the mole ratio by the molar masses. And when you're done with that, do the math, move your decimal point, and that gives you percentage by mass. Talked about empirical formulas. Remember, empirical formulas are the lowest whole number ratio of the elements in a compound. C6H12O6, the lowest whole number ratio is CH2O. On to chapter 5. A chemical equation basically describes a chemical change. We use a special arrow The arrow has the properties of an equal sign, saying there must be the same numbers and types of atoms on each side. Conservation of mass tells us that this also must be the same mass on both sides. In order to make sure we have the same numbers and types of atoms, we insert coefficients. Now, there are lots of different ways to try to balance equations. Hopefully, you've all practiced lots. You will have balancing on the exam. And if you've tried the quiz, there's lots of balancing on the quiz. You stick in coefficients, manipulate them until you wind up with the same numbers and types on both sides of the arrow. We talked about a series of reactions, reaction types. Synthesis reaction is very simple. You start off with two or more things, and you make something new. It's a synthesis, a combination reaction. Decomposition is just that, backwards. You start off with one thing, and you wind up with two or three things. Once again, you can do this with elements, or make elements. You can make compounds, whatever. You must start off with a compound, however, in decomposition. Single replacement. We said in a single replacement, there's a rule of thumb. We're going to have a compound and an element. We're going to make a new compound and a different element. In this reaction, if your element is a metal, it will replace the metal in the compound. If your element is a nonmetal, it will replace the nonmetal in the compound. There are two exceptions. Hydrogen and carbon both act as if they are metals. Double replacement, we're going to simply swap ions. In order for anything to happen, you must get a precipitate, that's a solid, or a gas. We talked about redox reactions. We looked at the full set of rules for oxidation numbers. Remember, oxidation describes the loss of electrons. If oxidation is the loss of electrons, then reduction is the gain of electrons. In a redox reaction, something must be oxidized and something else must be reduced. Remember, this says the same sort of thing. Oxidation, loss of electrons, reduction, gain of electrons.
I get confused with that. Just whatever I think I have to do that.
Just remember one of them. Remember, oxidation is loss. That's all. Remember one of them and you got it.
It's like the number will increase, right?
Yeah, don't worry about that. Just remember, you're losing electrons is oxidized. I always get confused if I try to think about numbers increasing and decreasing too. So, yeah.
I just got confused on that quiz because it was like, I didn't know, when you were asking if it was before or after, that's when it got confusing. And then that's what, you know, the balanced equation or whatever, or not balanced in terms of charge,
It's
but
still off.
I just, you know, I couldn't figure it out.
Well, on the in the slides here, the problems, we're going to have a couple redox reactions. So, you know, when we come to those, ask a question and we'll try to work through it. If we're trying to predict products in a reaction, that's when it's useful to know if it's synthesis, decomposition, single replacement, whatever. For a synthesis, first thing you need to decide is whether or not you're going to make an ionic compound or a molecular compound. It's really simple. Is there a metal involved? If there's a metal, it'll be ionic. If it's ionic, you just need to look at the common charges that that ion will have and build your compound. If it's going to be a molecular compound, instead of charges, you look at the valence. Basically, that's how many electrons it will gain in terms of making covalent bonds or lose. If we had carbon, carbon is group 4. It needs to gain 4 electrons to make this full octet, so it will make 4 bonds. That's its valence. If we have oxygen, it needs 2 bonds, etc. Single replacement, remember, except for carbon or hydrogen, metal, metal, non-metal, non-metal. Solubility, we all love that. There is a table, but you don't really need to remember the table, just a few key things. Remember, anything in group 1 or ammonium will be soluble. Anything that's acetate or nitrate will be soluble. Then you just have to remember a few sets of heavy metals that form insoluble halides or sulfates. Any questions? Go over these things, make sure you know them all. It really can help. It condenses it down to a couple of pages. All right. Very, very simple question. We're making tetraphosphorus decaoxide. We make that by reacting phosphorus solid with oxygen gas to give us P4O10. What is this type of reaction? It's a very simple question. All we're doing is taking 2 elements. We're making a compound. This is a simple synthesis reaction. Is this also redox? Remember, anytime you have elements on one side or the other, you're going to have redox. Because in order to go from an element to a compound, you have to do oxidation or reduction. So that's a real simple thing to think about. If you have elements on either side, the reaction must be redox. Sodium bromate. We didn't talk about bromate. Bromate is BrO3, just like chlorate is ClO3. All right, for sodium bromate, we have 4.68 moles, and we are given a molar mass. What we want to know is how many grams 4.68 moles represents. Think about this. Think about how simple this is. How much does 1 mole of it weigh? 150. Right? If 1 mole weighs 150, how much does 4 moles weigh? 4 times that. So 4.68 times 150, multiply moles by molar mass. Our moles here will cancel, and we should get about 700 grams of sodium bromate. You know how much 1 mole weighs. 4.68 is simply 4.68 times that. Now, isn't that so nice and simple? Yes. All right, let's look at this reaction. Interesting reaction, isn't it? We want to classify it. Is it a single replacement, decomp, double replacement, redox, or none? Kind of looks like it's synthesis, but synthesis isn't listed, is it? Well, it's not a single replacement, because remember, we need a compound and an element, making a compound and an element. We only have a compound. So single replacement is gone. Double replacement is stupid. Decomposition, we're going the wrong way. So is this redox? Now, what did I just tell you? If there's an element on either side, will it be redox? Absolutely. So let's prove it to ourselves. The iron here has an oxidation number of 0, right? It's an element. What's this iron?
This one, it's plus. It's because it's down.
It's
Oh, plus.
iron 3 sulfate. What's this compound? Iron. What's the charge on sulfate? Sulfate is -2. Therefore, this must be iron 2 sulfate. Iron has gone from 0 and +3 to +2. Therefore, oxidation numbers have changed, and this is a redox reaction.
Was the plus 2 because that was the 3 before the iron? That's why it was only plus 2? Or because iron in the second group of metals, it's always plus 2?
No, iron is transition metal, so it can be +2 or +3. Sulfate is -2 iron, right? For iron sulfate to be neutral, FeSO4, that means that the iron must be +2 and this must be -2. So that makes it iron 2 sulfate. Over here, we have sulfate, which is -2, right? And we have 3 of them, so that's 6 negatives. Our 2 irons must have 6 positives, or 3 each.
No, I understand because I was thinking like separately, I did like the oxygen and the sulfate. It's not, it's all together.
Yeah,
It's
they're
sulfate.
treated as a lump.
That's why it's true.
All right, we have 2.5 grams of methane, 16.04 grams per mole. Calculate the number of moles of methane. On the exam, this is actually based on an exam. That's where these questions all come from. This was a show your work. Okay, so that's why it looks like this. All right, what are we trying to do? We're trying to figure out the number of moles. We have a mass and we have a molar mass. Remember? What do we say before we go to bed every night? We say mass divided by molar mass is moles. Okay? Don't forget it. Mass over molar mass is moles. So what do we have to do here? All we have to do, take our mass, divide it by our molar mass. Now this was show your work, so you had to. 2.5 grams, 16.04 grams per mole. Grams cancel. Do the simple math, and there's 0.156 moles. We are looking at 3 significant figures, so that's right. Mass over molar mass is moles. There's another one that we'll do in chapter 7. Concentration times volume is also moles, but we'll do that one later. All right, this is fun. Let's balance this equation. I'll pause for a minute while you do it. If we were going to do odd and even, I would look right away and say 2 borons, 1 boron, right? So let's double our boron. Now let's see what we've done. We have 3 sodiums for every borate, right? Therefore, we have 6 sodiums here, right? This is the only place we have sodium, so we got to put a 6 there. All right, sodium looks good. Sodium is good. Boron is good. Hydrogen. Let's see. We have 6 hydrogens. We would need 3 waters. Do the oxygens work out? We have 6 oxygens, 7, 8, 9, right? We have 6 oxygens, 7, 8, 9. So yes, it really is balanced. Bless you. Any questions? Step 1. 2 borons, put a 2 here. That gives us 6 sodiums, put a 6 there. That gives us 6 hydrogens, put a 3 there, and then check to make sure oxygen works. As I recall, when I gave this particular question on an exam, lots of people missed this one. And I never quite figured out why. Copper 2 sulfate pentahydrate. This is a coordinate bond here, but this is a substance. This is a molecular, well, it's an ionic molecular complex right here. Okay? Covalent coordinate complex. So it's a unit, right? We want to know the mass of all of the oxygen in exactly 1 mole of this stuff. Okay? Now, so what's the mass of the oxygen in this stuff? We know that 1 mole of oxygen is going to be 16 grams, isn't it?
And so we have to do the ratio between how many oxygens.
Exactly, that's the only question. How many oxygens are there
So we have to
in this?
oh, 9.
9, that's what I get. 9 moles of oxygen. We know that every mole is going to weigh 16 grams.
So 9 times.
9 moles. So this is our stoichiometric ratio, our mole ratio, if you will. Every one of these weighs 16 grams. Simply do our math. 9 times 16 is 144. Make sure you see that there are 9. There are 5 waters attached to every copper sulfate. So 4 oxygens and 5 more oxygens. A total of 9. Oh, I love this question. I really do like this question. Which of the following is not a redox reaction? Now, what words have we said this morning twice so far about determining if something is redox or not? What do you look for? You look for elements. If there's an element on either side, then it has to be a redox because the element is going to a compound. So, if we look at A and D, we have two elements going to a compound. That must be redox. Must be. Down here, we have sodium going to a compound. That must be redox. So those two are out. Everyone see that? Any other one that's nice, simple, dead giveaway? How about this one? Oxygen is an element, isn't it? Oxygen is an element. We're making it from peroxide. It must be redox. So you don't have to sit and figure out all the little numbers here and there, do you? We can eliminate three of them just with our simple rule. All right, now we're down to two. We have one that's a single line and we have one that's huge. Which one do you want to work on? The simple one, right? Okay, we can do that. Let's look at this and let's assign oxidation numbers. Oxygen isn't going to change, is it? Hydrogen isn't going to change. We have sulfate, we have sulfate. Don't worry about those. Let's just look at the irons. Right? Just look at the iron. What is the oxidation number of iron in this compound? If oxygen is -2 and we have 3 of them, that's 6 negatives, right? Iron must be +3. Over here, sulfate is -2, right? Just like oxygen was. We have 3 of them, that's 6 negatives. That means each iron must also be +3. Therefore, this is not a redox reaction, and it is the correct answer. But just for jollies, let's look at the equation that took up 2 lines. Once again, sulfate isn't going to change, is it? The hydrogen isn't going to change. Oxygen isn't going to change. So the one we have to really worry about is going to be manganese and iron. So let's just take one of them and see if its oxidation number changes. Okay? Permanganate. Look at this guy right here. We have 8 negatives, right? Right? We have 1 positive, which means manganese must be +7. 7 positives, 7 + 1, that's 8 positives, 8 negatives. All right, down here with manganese sulfate. Sulfate is what? -2. That means that manganese must be +2. Has manganese changed? Yes. Therefore, this is redox. Once again, you don't have to waste your time doing oxygens, doing sulfates, doing hydrogens, things like that. They're not going to change, typically, if there's other stuff that can change. So, focus on your metals. Any questions? I really like this type of question. If we did the irons, we would see that iron changes from +2 to +3. Which one has been oxidized? Which one lost electrons? Which one gained electrons? In order to go from +7 to +5, what does manganese have to do?
Lost.
It has to gain electrons, doesn't it? So it's been reduced. And that means the iron, as it went from 2 to 3, lost in electrons, has been oxidized. Here we have sodium sulfate. We have 29.34 grams of it. How many oxygen atoms are there in 29 grams of sodium sulfate? Well, we know its molar mass, right? It's 142. So if we had 142 grams of sodium sulfate, it would have 4 moles of oxygen, wouldn't it? And we know that every mole of oxygen would be 6.02 times 10 to the 23rd atoms. So that makes sense, right? Here we have 29 grams. What we need to do is to figure out how many moles this is. Once again, we have a mass, we have a molar mass. What do? Divide them, and that gives us moles. Once we know the number of moles of sodium sulfate, we know that every mole is 6.02 times 10 to the 23rd things, and that there are 4 oxygens. So we can set it up like this. Mass divided by molar mass is moles. Every mole is 6.02 times 10 to the 23rd, and there are 4 of them. Once again, before exam time, please make sure you have your calculator and you're real happy with it and it's happy with you, so that you can do these sorts of things, get the answer that you expect, know how to interpret that, etc. This should be about almost 5 times 10 to the 23rd. Any questions? We're looking for moles. We have a mass. We have a molar mass. How many times do I have to say this? Mass divided by molar mass is moles. So all we do is take our 47.51 grams divided by 101. We're working with 4 significant figures, and this is 0.4660. Once again, a very trivial question. We just said this was a covalent coordinate compound, right? So we're starting off with a compound here. We are making two compounds. We are simply decomposing it, aren't we? Is this redox? No. Calcium is still calcium, chlorine is still chlorine, water is still water. So this is a decomposition that is not redox. Percent composition, mass percentage. We have a compound with chromium and silicon. Is this an ionic compound or molecular? Does it have a metal? Absolutely, chromium's a metal. So it's an ionic compound. Mass percentage of chromium. Well, chromium is 52 grams per mole. This stuff is 212 grams per mole. Remember, when we're going to do mass percentages, what we do is simply write the mole ratio. Then we're going to convert that to a mass ratio. Do the math, move our decimal place, and we're there. Right? Our mole fraction, mole ratio, in every chromium to cyanide, something like that. And every one of those guys, we have 3 chromiums for every one of these guys, right? Every chromium weighs 52, and there are 3 of them. One of these weighs 212. Simply do our math. 3 times 52 divided by 212. Move our decimal 2 places to get percentage, and round it to 73.52. You will have to do this on the exam. Please make sure it's not difficult. Mole ratio, mass ratio, and then just move your decimal. Oh, you hope there's a lot of these. Which of these are least soluble? What can we rule out right away? Acetate, nitrate. They're always soluble, aren't they? Sodium, always going to be soluble. So we're down to 2. Iron 2 chloride, lead 2 sulfide. Most halides are soluble, right? Except for silver, lead, mercury, and copper. This is not one of those. Therefore, the one that is not soluble is going to be lead sulfide. Remember, sulfide tries to be just like oxide. The oxides will be insoluble, so will the sulfides. All right, the oxidation number of sulfur in this guy. Well, on the exam, you'll have it two ways, I think. You'll have something that looks like this, and you'll have to enter the numbers, and or you'll have multiple choice. Same thing. So, let's start here with what we believe in, and that's going to be our oxygen and our sodium. The oxygen is going to be -2, isn't it? Our sodiums are going to be +1. So we have 2 times 5, 10 negatives, right? We have 2 positives. Each sulfur must be +4. Ten negatives, 8, 9, 10 positives. Again, make sure you get this because this is going to be important. Same sort of question again. We have 78 grams of potassium dichromate. We want to know how many chromium atoms we have. Every potassium chromate has 2 chromiums, right? So that's our mole ratio. Yeah.
I don't understand how you got +4 for the last one. How you got +4 for the last one? I don't understand.
It says right there.
Yeah, but I was like adding.
Okay. Oxygen, we said, was going to be -2,
Okay.
correct?
Yeah.
So we're happy with that one.
Yes.
How many negatives do we have in this molecule? We have 10 negatives. There's 5, and they're each -2. Now sodium, group 1 metal, is always going to be +1, right? We have 2 sodiums, so that's 2 positives. So we have 10 negatives and 2 positives. We are missing 8 positive charges, right?
Okay.
And we have 2 sulfurs. So it must be 4. All right, back to this guy. 2 chromiums in every dichromate. We have a mass. We have a molar mass. That gives us moles, doesn't it? If we know how many moles we have, and we know how many chromiums there are in every mole of this stuff, and we know how many things there are in a mole, we can do that. Our ratios. We would calculate the number of moles. We would convert that to the number of atoms. And we would use our mole ratio here, 2 chromiums per potassium dichromate. Mass divided by molar mass is moles. Okay? Every mole is 6.02 times 10 to the 23rd chromiums. And every dichromate has 2 of them. Grams and moles both cancel. Once again, make sure you can do this math reliably. 78.8 divided by this times 2 times 6.02 times 10 to the 23rd is about 3.227 times 10 to the 23rd. figure up how many moles you have. That's this one. Every mole has 6.02 times 10 to the 23rd. And there are 2 chromiums per dichromate. Oh, this one was a gift. Where is barium on the periodic table? Just about right there. It's a group 2 metal. It will be +2. Sulfate. We all know sulfate is our friend. It is SO4, and that is barium sulfate. It's insoluble, isn't it? Barium and calcium. And what's the other one? Mercury? One of the others. All right, this is a very fun equation. Balance it. Well, I'd kind of begin at the beginning here. We have 3 hydrogens and 2 on this side. So this is odd, that's even. Let's even things up by doubling it out here. All right, now when we've done this, we have made 6 hydrogens, haven't we? They're going to show up in our water. That means we would need 3 waters, right? Again, we've doubled our ammonia, which means we have 2 nitrogens. So we're going to need 2 of these guys, right? Now, how many oxygens do we need?
5, what is ammonia?
We need 5 oxygens, don't we? 5 oxygen atoms. But unfortunately, they come in pairs. So what do? We can't put 2.5 here. We could, but that wouldn't be right. Therefore, let's double everything. Double everything. This is going to be 4, that's going to be 4, that's going to be 6. Now, how many oxygens do we need? 6, 7, 8, 9, 10. And now we can stick our 5 O2s in. Wasn't that fun?
Is there like a specific method to like know like what numbers to put
Method
first?
to my madness?
Yeah. Yes.
No, well, you know, again, look at what we did. I just started here, okay? And I said we have 3 hydrogens, odd number, even number. So that won't work, will it? So the way I do it is I just say, all right, let's make this even. Now let's see what happens. We put in 6 hydrogens, so we need 3 waters. We put in 2 nitrogens, so we need 2 NOs, which means we would need 2.5 O2s. Can't have 2.5. So let's double everything and make it 5. There are lots of different ways to balance equations. I think that this is the simplest for me. We're working on odds and evens and then just doubling if you have to. Sometimes you have to double twice. Okay, that was so much fun. Let's do another one. Well, this one, instead of doing odds and evens, when I just start here, things don't actually look so bad. We have 3 oxygens, we have 3 oxygens, have a carbon, we have 4 hydrogens, but we only have 2. Right? So let's start off by fixing that. 4 hydrogens, 2 hydrogens, let's double this. Now what we have done is we have made 1, 2, 3, 4 oxygens on this side, and we only have 3 on this side. Right? So let's double this. Now our oxygens are even again, but our hydrogens are off again. Now we have 4 times 2 is 8. Only have 4 here. So let's double this again. All right, let's see where we are. We have 2 carbons, don't we? So we need to put a 2 here. And finally, let's see how many oxygens we need. 1, 2, 3, 4, 5, 6, 7, 8. We have 2 here, so we need 6 more, right? And that does it. Let's take all this away and do it all over again. Everything balances out just as it's written, except for the hydrogens, right?
Yeah.
We have 4 hydrogens, we only have 2. So let's fix that. Now by fixing that, we've messed up the oxygens. So we need an extra oxygen, so let's double it here. Now by fixing the oxygens, we've screwed up the hydrogens again. We now have 8 hydrogens here, only 4 here, so let's fix that. If we have 2 methanols, we're going to get 2 CO2s. And finally, we just look and see how many oxygens we need. And that turns out to be 6 more, because we have 2. 6 more gives us the same thing here, and we're balanced. How do you learn to do this? Well, the sheet had 51 examples. Okay, that's how you learn to do this. Just do them over and over and over until you're sick of it. But by then you know it. All right, here we have a net ionic equation. We have thiosulfate reacting with iodine to give, I forgot what this is, S4O6, 2 iodines, and 2 iodide anions. we want to know which of these species in this thing was oxidized. So here we want to look at our oxidation numbers. Now this is an exercise, again, that's very important. And I particularly picked this problem because I thought it would be a neat thing to look at. Let's look at thiosulfate. And I want you to give me the oxidation numbers of the sulfur and the oxygen. Now let's do the easy one. What's oxygen going to be?
4.
No,
Negative.
it's good. Oxygen
Negative
itself is going to be minus 2.
Oh, yeah. The whole thing.
All right, now, remember thiosulfate is a dianion, isn't it? So let's ask the question. We have 3 oxygens at minus 2 each, right? 3 oxygens at minus 2. That's 6 negatives, right? But we have to save 2 of our negatives for our charge. So really we only have 4 negatives to work with, because 2 are going to go outside our bracket, and we're left with 4 inside here. So if we need 4 positive charges and we have 2 sulfurs,
Positive.
the sulfur must be plus 2. 4 positives, 6 negatives, minus 2 left over. Please make sure you get this. Get how to do this. We have 6 negatives in here. We have to save 2 for our charge. That means we're working with only 4. So we need 4 positives. Each sulfur must be plus 2. All right. So that's plus 2. Take this guy, S406, 2 minus. Do the same operation. I have it in words down there. What is the oxidation number of the sulfur?
Well, that's not, because it's going to be
How many negatives do we have total?
negative 10.
12?
We have 12 total.
But after all,
We have to save 2 for our charge. That gives us 10, right?
here
We have 4 sulfurs and we have 10 charges. What is the charge on the sulfur?
10 divided by 4 is
10 divided by 4 is
2.5.
2.5. Now we've seen a fractional oxidation before, haven't we? Remember a superoxide with minus 1/2? So we've seen that. We're not surprised. Again, think about the logic here. We have a total of 12 negatives. We have to save 2 of them for the charge. So we have 10 negatives. We have 4 sulfurs that must be worth 10 positives. So 10 divided by 4 is 2.5. All right. Has the thiosulfate been oxidized or reduced?
Okay.
Has it gained electrons or lost electrons? To go from plus 2 to plus 2.5, it has to lose half an electron, doesn't it? If it loses an electron, it is oxidized. Remember the really confusing nomenclature. If this is oxidized, that makes it the reducing agent. It's the thing that does the reducing.
And then most of the time is the second part. Do you have one when there is positive charge, like we did with negatives? You know, like we did with negatives?
If you have a positively charged
Then you
polyatomic, yeah, you could do that. Like ammonia, that's the only one that you would.
because I think I did see something with the positive one.
All right, the number of hydrogen atoms in 0.05 moles of this stuff is what? We know that in every mole of this stuff we have 8 hydrogens, correct? So our mole ratio is going to be 8 to 1. We know that every mole is going to have 6.02 times 10 to the 23rd things. And we have 0.05 moles. Convert the number of moles to atoms. That's this times 6.02 times 10 to the 23rd. Then our mole ratio is simply 8 to 1. This will do it for you. 0.05 moles times 6.02 times 10 to the 23rd. And our mole ratio is 8 to 1. Moles cancel. 6 times 8. We have 2.4 times 10 to the 23rd. And our very last one here. Let's classify this reaction. Now this is simple, isn't it? We have 2 things, we're making 1 thing. What does that make it?
Synthesis.
A synthesis. But, did I really mess up? Is this a redox reaction? All right, let's look at it. Sodium is going to be what? Going to be +1. It's way up on our list, group 1. Going to be +1. We have 2 sodiums, that means oxygen is -2. Oxygen is -2. Hydrogen bonded to a nonmetal is +1. And let's look at the other side. Sodium is still group 1, isn't it? It's still going to be +1. Hydrogen is still bonded to a nonmetal. It is also +1. Oxygen is still oxygen, and it is -2. This is an example of a synthesis reaction that is not redox. Now, the last time I taught this course, and I can't do this on this exam. Shoot. What I did was I took this exact same question and I changed synthesis to none of the above. So you had to decide if it was redox or nothing. And of course it's not. Everyone sees this. Everyone happy? On Monday, we will do the sample exam, just like we just did this one. Please work it by then, all right? Please work it.